So, is this image strike you as something familiar? It should, okay. It's a section through a muscle almost, we have done it, okay. So, you can identify the what? The I band, hello, the A band, okay. At the center of the I band you have the Z line, okay. So, you have a sarcomere, and you know that from the Z line you will have the actin filaments and then the myosin filaments, and then the sliding will happen and the muscle will contract. But this is not the skeletal muscle, this is the picture of a cardiac muscle. So, what we will do now is look at we will move on from the skeletal muscle, we move to the cardiac muscle, and you will find that there are a great deal of similarities, but some very relevant differences, and I will try to underscore them in due course of time. So, this is the aim of this slide is to basically emphasize that it is a very similar structure. We have seen this slide, we know smooth muscles that at the end we will talk about it, skeletal we have done, and today we are trying to focus on the cardiac muscle. So, here is the heart. Is the heart there? It's a very familiar structure, you have studied it on several occasions, okay. We will talk more about it, and it is made up of certain cells which we call as cardiomyocytes. Myo refers to muscles, cardio refers to heart, cardiomyocytes. Cytes refers to cardiomyocytes, okay. And these cardiomyocytes are they are arranged in a very interesting way. I see the whereas the cells in the skeletal muscle were simple guys, you know, straight cell goes to one end, communicates with or talks to the ligament, and the ligament talks to the bone, very simple state. In the architecture is slightly different. Here is a cell, okay, and then it branches, and it then communicates with another cell, that another cell then branches. So, you will have a structure in which you have the cells which are bifurcating and joining, and they form a sort of lattice work. Okay. So, this is a very interesting structure, and it is very relevant, and that is okay. And to exemplify that point, we have this image where you can clearly see what? You can clearly see that this is a cell, but this cell divides, and then this cell meets at another cell, and that cell again divides, and so they go on digressing, and they go on meeting, and they form a sort of lattice work. The second point that you would notice is that in the cell, okay, so you know there is a nucleus, and there is a sort of a partition which we call as inter-calated disc. Now, this word is coming for the first time, we did not have it in the skeletal muscle. What word am I using now? Inter-calated disc. These intercalated discs are very interesting because gap junctions, hello, gap junctions, okay. Gap junctions are proteins, okay. They are made up of 6 subunits. How many? 6 subunits, and they are the junctions by which one cell can just communicate to another cell. Okay, so I am sure you have learned the purpose and the functioning of the gap junction, whereas if one cell is stimulated, the ions will simply pass from one cell to another cell So, it is actually an electrical synapse. What is gap junction? It is electrical synapse. So, if this cell is stimulated, then it can stimulate that cell, it can stimulate that cell, it can stimulate that cell. But if it goes in that order, hello, if it goes in that order, then the next cell, follow the line, next cell will fire a little later, hello, and the next cell will fire a little later, and the next cell will fire a little later. Okay. So, in that way, in every bit I can program as to which cell should fire before which, and the next which, and the next which, and the next which. Okay. Please keep this thought with you, because that will be very helpful when we try to understand the process of systole and diastole. Now, whereas in the case of the skeletal muscle, it was very simple, the bone would anchor on ligament and on the bone. Now, here with the heart, okay, it is not a skeletal muscle, okay. So, it does not go on any bone, okay, it goes on, as if it goes on itself, okay. And to highlight that point, we have, I am sure you can identify the heart. So, this is an auricle, that is another auricle. So, these bands of, or the fascicles of muscles, they go this way, and one of the most interesting points is, I look at this fascicle, you know, this fascicle is what is making up the ventricle, hello, making up the ventricle. It goes like this, look at the arrow, and then it folds on itself and it goes this way. Okay. So, that when because of that particular architecture, when the whole muscle contracts, you are going to get the reduction in the volume of the ventricle, increase in the pressure, that is how the blood will be pumped out of the ventricle. Are you with me? So, it is a sort of a bag, okay, but that bag can relax and the bag can contract, and it is possible because of this particular arrangement, and then of course, it is involuntary. Another major difference from that of the skeletal muscle. Okay, skeletal muscle you can control, these muscles you can control. Then who controls and what controls them? The answer to that question is the heart muscles control themselves. How do they do it? We will see a little later. Okay, they have a particular rhythm and they keep on beating in a particular rhythm, and that is possible because they have a very specialized tissue within themselves, which call as step back pacemaker. What do you call them as? Pacemaker. What pacemaker? SA node and AV node. We will talk about it a little later. But this image is again very interesting because as a heart, I take a tiny piece of the heart, I can blow it up and I can see the cells, I can see the intercalated disc, and along the intercalated disc I can see the gap junctions. Here the gap junctions are what? Here you see a magnified view. So there is one cell, there is another cell, there is the intercalated cell, there is a gap junction, and if this cell is depolarized means there are more ions going in. Okay, inside earlier was how much? Let's see, minus 85 millivolts. What did I say? Minus, say that again. Minus, what is this minus 85 millivolts? I will take a single cell from the heart and put an electrode in it. Okay, and try to measure what is the potential difference between inside to outside, and I'll find that the inside potential difference is how much? Minus 85 millivolts. How much it is? Minus it in comparison to the outside, which I will consider as 0. So outside is 0, inside is minus 80, and if one cell is depolarized, it means there is increase in the positive ions inside. The positive ions can flow from one cell to another cell by way of the gap junction, and the other cell will also respond, and then the other, and then the other, and they can sequentially go on in a definite order. So we are again looking at a single cell, and this looks again very familiar, and what is most familiar is the occurrence of, okay, you can see the actin myosin filaments, they are there, there is a, from here to here is a Z disc or it is a sarcomere, absolutely no problem, and then you have the mitochondria there and the endoplasmic reticulum, hello, same structure, but here you will, I will draw your attention to two major issues. Number one, the t-tubules, they are there, okay, but these t-tubules are much bigger in diameter. Okay, how much bigger? Bigger with reference to what? With reference to the t-tubules which you will encounter in the skeletal muscle. These are almost 5 times larger in diameter. So skeletal muscle is larger in diameter, but 5 times larger in diameter means the total volume will be about 25 times more. Hello? Okay, so volume will be more. So these t-tubules are much larger as compared to those that we encounter in the skeletal muscle, number one. That is the t-tubule. It's much larger. Okay? Now, the t-tubule is having a large number of, okay. So when you are in the t-tubule, you are extracellular, hello? You are extracellular. So if you are in the t-tubule, you will encounter a large number of glycoproteins, and those glycoproteins can bind to a large number of calcium ions. So there is a huge supply of calcium ions, where extracellularly, much more than you will encounter in the t-tubules in a skeletal muscle. Okay. Then the second difference that you find is the endoplasmic reticulum, okay, which played a very important role in the case of skeletal muscle. Why? It would suddenly release the calcium ions whenever the information will come. How? By way of the action potential along the plasma membrane. Okay, then DHPR, hello, DHPR, and then the DHPR talking to the RYR. What am I talking about? Rhinodine receptor, okay, and then it will open this endoplasmic reticulum, and the calcium ions will flow out, and that's here again the endoplasmic reticulum is much less developed. So I find a clear difference between the skeletal muscle and the cardiac muscle. Here the t-tubules are very large and the endoplasmic reticulum is little small. So main source for calcium ions, main, I am not drawing a hard and fast line. Main source for calcium ions in the case of skeletal muscle is endoplasmic reticulum, done. But in the case here, okay, endoplasmic reticulum plays a little subsidiary role, mostly large volume comes from outside. And for that reason, we will find that the t-tubules are much larger. Okay, so there is a fundamental difference between the organization of what and what, the t-tubules and the endoplasmic reticulum that you will find in the case of the cardiac muscle. So here we have again, I have put the image of cardiac muscle, you can see that, and I take single cell from here, okay, single cell from single compartment, and I will impale, and I will use the right word, I am going to impale an electrode. Can you see that image there? Impale an electrode. And what is that electrode there? Actually, it is a glass capillary. Okay. In earlier days we used to use more metal electrodes, but metal electrodes have a problem that the ions leach and they damage your preparations. So, these days we do not use metal electrodes, we simply use glass capillary, and glass capillary is filled with, when you said glass capillary I was so happy, I thought you will answer my second question also. It is filled with a conducting solution which is nothing but concentrated KCl. What did I say? Say that again. A capillary which is open at the tip, it is open at the tip, and you know these days the techniques are so fine that the tip is less than a micron, hello, less than a micron, okay, and then you fill it up with potassium KCl solution strong, and then you put in that you put a wire, and then you connect that wire to oscilloscope or whatever you have, galvan, whatever you have, and so you have one electrode we will use the right word, impale it across the plasma membrane inside. So, you are comparing the potential difference across what is just below the plasma membrane and what is outside the plasma membrane, and you find that the difference across the two happens to be how much? Minus, inside is minus 85 millivolts, is that right? Okay. And now I am going to record it, and this muscle cell of mine is, let us presume that it is behaving like a, as if it is in a full heart, and it is what? It is beating. It is beating, it is mechanically beating, okay, and it is beating because it is showing a rhythmic change in the potential, a rhythmic change in the potential. How many, on an average, how many beats would you expect in this preparation of mine? 72, let us say, 72, average 72, okay, you can debate if you like, but it is 72. It is what? 72 beats average, okay, because that is the number of beats we have, okay, the pulse rate is maybe 67, 72, okay. Now, when we find that, when you are, so what am I doing? I have implanted an electrode in a single heart muscle, okay, and I keep on looking at my oscilloscope or my whatever meter I have there, and I find that to begin with the potential difference here is about 80 here, 85, 80, whatever, it is here, and then suddenly it shoots. Okay, and it goes how far? It goes almost to plus 20. So, inside for a very short period of time, inside has gone to, inside has become plus 20, which means there is a reversal of polarity. Cell is completely depolarized. And then I find that it remains, there is a slight decline, but almost remains like a plateau, and then suddenly it drops and goes back to the baseline. And that the plateau remains for about 0.2 to 0.3 seconds. How long does it remain? Now, remember these words, 0.2 to 0.3 seconds. Actually, if you have taken a cell from the atria, the plateau is for a period of 0.2 seconds. Absorbed, you got the point? If I take that cell, single cell from the ventricle, then the plateau remains for a little longer, it is about 0.3 seconds. Now, this happens to be extremely slow if I compare it with the electrical response of a skeletal muscle. I am going to our yesterday's talk, earlier talk, in which we do the same experiment, we impale an electrode into a skeletal muscle, and we find that to begin with the resting potential is about how much here? Skeletal muscle, this skeletal muscle, how much is it? Minus 90 millivolts. And if you excite it, what should be your method of exciting it? How can you excite it? Yes, say that again. Conductance, oh good, simple in the light of what we did in the previous lecture. One way would be, you see, the skeletal muscle cell won't respond on its own unless you stimulate it, and one way to stimulate it is to go to the nerve that goes to the skeletal muscle, put your electrode and stimulate the nerve. Once you stimulate the nerve, then the nerve will release what neurotransmitter at the terminal? Good. Or I can directly give acetylcholine. Works beautifully, give acetylcholine, it stimulates, okay. So you can give acetylcholine, and I find that then the cell responds. So it's going to show the depolarization, it goes to about almost plus 35. Look at that image, how far does it go? Inside will go to plus 35, and then it rapidly comes down. Okay, now I want you to look at that image, that the lower one where I am showing you the tracing of the skeletal muscle, and you tell me what time period does it take for the upshoot to happen and for it to come back to the resting position? Point what? 0.3 what? 0.3 what? Millisecond. Now can you compare this with this? This was how much? 0.3 seconds. Okay, okay, have you let it go deep in your brain that there is huge difference, that whereas a nerve and a skeletal muscle, they work in terms of milliseconds. The cardiac muscle works in terms of 0.2 or 0.3 seconds. So you can see how many fold the response of the cardiac muscle is slower as compared to that of the skeletal muscle. Okay. Now let's see why this response, why are we finding this response from the cardiac muscle. Number one, the plasma membrane of the cardiac muscle is equipped with different kinds of ion channels. Got the point? Different kinds of ion channels. And some of them are called as fast sodium ion channels. Say that again. Fast sodium ion channels. And fast sodium channels are really fast because they open and close within the time frame of 1 upon 10,000 of a second. Hello? 1 upon 1, 0, 0, 0, 4 zeros, 1 upon 10,000. Are you with me? It will open and close, open and close. You can't even, how quickly that happens, we can't even imagine as to how much is that. And that means what? The cell has been stimulated, those sodium ion channels will open and the sodium will go so fast that, and so much sodium will go that within a period of so much time, there's hardly any time, it just shoots. And starting from minus 85 inside, it will go to how much? It will go to about 20 or so. Step number 1. Okay, opening of the fast sodium ion channels. Okay, this is followed by second type of channels, which we call as calcium channels or slow sodium calcium ion channels or DHPR. Hello, DHPR. They are very familiar, we know them. What does DHPR stand for? Dihydrox, not C, dihydropyridine. Okay, yeah, receptor, very good, very good. So, and therefore calcium. And we also had another name for this, L-type, hello, L-type. Why did we give the name L? Long lasting, which means they are slow. Okay, so it is, whereas the sodium ion channels open and they immediately depolarize the cell. Okay, then a little later the L-type calcium ion channels will open. They will allow they are voltage gated, they will allow the calcium ions to go through, and it's a slow process, and because of that the cell, inside of the cell, okay, it remains depolarized for about 0.2 seconds if you are in atria, 0.3 seconds if you are in the ventricle. Okay, and after that, meanwhile those sodium ion channels have already closed because they are open for very transient period, and over a period of 0.2 or 0.3 seconds the L-type calcium ion channels are also closed. Yes. Which one? No, inside, to begin with, how much was the potential inside? Minus 85. Sodium ions came in, as a result of that it went where? Plus 20. Inside is plus 20. Okay, and then calcium ions keep on pour in, they also take positive ions. So the positivity remains there for a period of 0.2 to 0.3 seconds. Okay. No, it doesn't go higher. If your answer to that question is sodium ion channels have closed. Sodium ions are already inside, but the pump is also working at the same time. Okay, it is eventually the okay. I cannot answer your question, but say that whole thing put together. Okay, the sodium ions shoot there, then the calcium ions come. Actually, calcium ion is also not able to make an absolute flat plateau. It keeps on going down, and then potassium ions start opening. Okay, and now the reverse will happen. Okay, in what direction will the potassium ions travel? From inside to outside, they will take the positive charge, and as a result of that, this will again fall to the basal level. So what are we essentially saying? We are seeing the interplay of 3 ions. Okay, sodium will take it up, calcium will maintain there or slowly drop, and the potassium will bring the potential difference inside again to minus 85. Are we okay so far? Which one?
When the voltage is declining.
That's a very interesting question. What is making the potassium ion channel open at that particular time? These are all voltage gated ion channels, and their operation depends on the typical voltage which you provide to the membrane. So when the cell goes to that particular membrane, as a result of what? As a result of the maybe closing of the calcium ion channels, whatever potential difference develops at that moment, that is good enough trigger for the potassium ion channels to open, and when they open, the rest of the story will follow. Okay, so never forget why are these channels responding? They are only responding to the voltage. Okay, so voltage will determine whether the channel will open or not. Okay, all right. Now I'll superimpose on this. Let us take a look at this image. What does this image tell? This is a very interesting image. Follow this image. Let's try to understand. We are trying to trace the transport of ions across the membrane. Okay. Now we already know, or maybe if you don't know, I'll inform you. The plasma membrane, whether it's a skeletal muscle or it's a nerve cell, it has a large number of, I am using a different term, leakage channels. What channels? Leakage channels. So what am I talking now? I am talking of potassium ion leakage channels. What am I saying?
Potassium ion leakage channels.
Are these channels sensitive to voltage? No, they are not sensitive to voltage. Will these channels, when they open, will they allow the flood of ions to go through? No. These are the channels which allow one ion to pass through at a time, one ion. Okay, one ion. And since it is a leakage channel, the name itself means that in which direction will the potassium ions leak?
Inside to outside.
Inside to outside, hello? No confusion there. It will leak from inside to outside. Okay. Now, whatever is the amount of sodium ions leaking because of the presence of sodium, I made a mistake, because whatever is the, let me recompose my sentence, whatever is the rate at which the potassium ion channels are leaking, whatever it is, I'll call it as 1. What will I call it as? 1. And if I call that as 1, then I want you to look at the graph and tell me whether the leakage channel for sodium are they there, and if they are there, are they as efficient as that of the potassium ion channels? It's here 0.1. What does it mean? In a resting stage, the rate at which, so the number of sodium ion channel leakage channels is far less. Now, this is a universal truth. Remember this everywhere. Okay, in any given nerve cell, in any given muscle cell, the rate at which potassium ions are leaking out is much more compared to the rate at which this. In what direction will the sodium ions leak? Outside. That's much less. Now, as a result of this cell being stimulated, you suddenly have what is the first response? Opening of the fast. Use the word fast. Opening of what? Voltage gated fast sodium ion channels. Okay. As a result of that, can you see that yellow spike there? It goes beyond our graph. Okay, and it rapidly comes down because the sodium ion channels are open for a very short time. Are these leakage channels? No. They'll just open. They'll 50,000, 100,000 ions will very rapidly go within milliseconds. Okay. A little later, I am drawing your attention to the red line. What does look at the image and tell me what does the red line represent there? Calcium. We are talking about the calcium conductance. As long as the cell was in a resting stage, the calcium conductance was very low. Okay. As a result of the entry of the sodium ions, and as a result of that, whatever voltage has changed, that has stimulated the DHPR. As a result of that, DHPR open, and as a result of that, you can see the conductance of the calcium ions across the plasma membrane, which goes so far. Why do you think calcium ions are flowing in? More outside. Calcium ions are far more outside. Does anyone remember as to how much of calcium ion, what is the ratio of the calcium ions outside to inside? It's too important, you just can't ignore. 35 was potassium. Inside is more outside compared to. You are all making a mortal mistake, a terrible mistake. Listen to this. If you just compare the ionic concentration of calcium outside to inside, outside may be 1,000 to 10,000 times more than inside. Do I have to shout more to emphasize? What did I say just now? Outside calcium ion concentration is 1,000 to 10,000 times more. There's an enormous gradient, enormous gradient. And you know one of the reasons why the gradient is so large? Because in the cell, when I say in the cell, I am excluding the endoplasmic reticulum. Are you with me? In the cytosol, a calcium ion is an extremely rare commodity. You don't find it, the concentration is extremely low. 10 raised to the power of minus 7 m, very low, calcium ion. Now, can somebody please stand up and tell me as to what is the physiological significance of keeping the calcium ion concentration so low in any cell? Endocrine cell, nervous cell, muscle cell, it's low, 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 low. It's so low. Why is it so low? You know the answer. Secondary? Secondary, yeah, that's a part of the answer, but you are not hitting the nail on the head. Why? You are right, It is such a critical molecule. What is such a critical molecule? Calcium is such a critical molecule that you better control its concentration. Hello, are you with me? So, if you want to control anything, you give calcium. But does it mean that you can allow the concentration to rise? No, everything in the cell will go haywire. No, nothing. You have to make sure that such a critical molecule like calcium, which has such an important role in 100 biochemical reactions, you better make sure that it's not available in the cytoplasm in very low concentration. So when you want something to be done, okay, you allow a little calcium. When you want to actin-myosin, okay, when you want insulin to be released, you want to saliva to be released, you go to any cell, okay. Whenever you want to change its you want to respond, give a little calcium. But a little calcium may mean it has gone up by 1,000-fold. Why has it gone 1,000-fold? Because initially the calcium ion concentration was so low that a little could mean 100 times, 1,000 times. Are you with me? Okay. So the beauty of the biology is to make sure that the calcium ion concentration in the cells keep it extremely low. When you want anything, give a little. That little, maybe 1,000-fold more, 1,000-fold increase, okay, and then you can okay. So here you so the voltage gated calcium ion channels will open and they'll stay open for some time and then they go down. Something very interesting is happening with the potassium ion channels, voltage gated. Because of this depolarization, okay, so we have already seen what? The potassium ions are leaking. At what rate? I don't know, I'll call it as 1. When the sodium ion channels open, okay, that very moment, the voltage gated potassium ion channels are inhibited. Therefore, the conductance of potassium ion goes down. Okay, and it goes a little up and then it goes a little beyond, and when it goes a little beyond, this will come down and the cell is now completely repolarized. So the cell goes through the cycle of getting depolarized, going to the peak, assume a plateau where the cell remains depolarized while potassium ions will go out, they will take with them the positive charge, so that the positivity outside is again restored and the cell will come back to the resting potential. Yeah.
Does voltage gated channels only depend on voltage, or do they have an additional factor that also, like along with voltage?
Oh no, they depend only on voltage.
So when the potassium, like if you look in the graph there, when the potassium opens, even before the potential reaches a higher point, so even there it crosses that threshold.
You mean this? You mean?
No, in the left.
This image?
Yeah, so it's the potassium channels are getting stimulated at some like line. Like let's say,
in this point you are saying?
yeah, it's stimulated at 0. It's crossing 0 2 times.
This is not potassium, no?
No, this total.
This you mean? Okay, this one, the blue, the purple one you are talking. Oh, tell me about purple. Yeah.
The blue one.
Yeah. Tell me.
So then, let's say it gets opened at 0. It's opening at twice then.
Twice means I am not getting.
Like in the front also at 0 seconds also it gets stimulated once, and once also at 150 milliseconds or whatever.
You are talking about calcium ions, right?
Potassium.
You are talking about potassium ions.
Yeah.
Okay. So in this we don't talk about potassium ions, right?
No, but
I am not getting his argument.
What-
In this or that the one.
Starting to fall when voltage gated channels are open.
Mm-hmm.
So that threshold voltage
Hmm.
is being reached even before that point in time.
Yeah, that's what.
Threshold for potassium.
So when
Okay, okay,
things
okay,
sodium
okay,
channels are open,
okay,
crossing the threshold
okay.
at which the potassium channels are later opening on. So
The-
while they're opening on when the sodium is
The answer to that question relatively, I got your question now. The answer to that question is the calcium ions, voltage gated calcium ion channels do take a little time to open. Yeah, no. They are slow to start, continue to remain open and then go. Okay, that's their nature.
So, if the calcium ion channels are slow to open, why didn't the potassium ion channels open? Because it's the same instead of the calcium. So here, because calcium is opening, the potassium is getting like permeability is getting decreased. But why didn't this open first?
Look, it is the dynamics of all these proteins. Okay, and actually at that moment the potassium ion channels are actually closing. Just see the potassium conductance here. What is happening to the potassium conductance?
That is because the calcium is opening. Right?
Yes. No, it is all put together. It's all put together. Okay. The answer lies somewhere in the response of the channel voltage gated channel proteins to open with reference to time. It's voltage plus time. Okay, means the same. I can give the same answer which I gave there. When would the potassium? What would be the response of the potassium ion channels? First they will get inhibited at that. Okay, and then eventually So we have to look at the proteins of the sodium ion channels, potassium ion channels, and the chemistry of each with reference to how and when they respond to the voltage and at what time scale. Your answer is hidden somewhere in what time scale. Are you getting the argument? Right.